First of all, I would like to thank the invitation. I always want to visit this campus, and I finally made it. And I'm very excited to give this talk. By the way, if you have any question during the talk, please just feel free to ask the question to stop me. I think there are lots of questions that we're discussing in this topic. So this is about construction of robust confidence interval. It is a joint work with my wonderful collaborator, Yuetian Luo, who is currently a data science postdoc at U Chicago. He has been doing some amazing work during the past 2 years, and he will join Rutgers as an assistant professor very soon. I'm going to start a talk with this very simple example where we observe ID Gaussian data, and the goal is to construct a confidence interval for the location parameter theta. Okay, and the problem has a standard solution that is given by this interval, which is centered at the maximum likelihood estimator x bar. The radius of the interval is of order 1 over root n, and from our classical statistical theory, we know that not only does this interval covers the true parameter with probability 95%, but among all intervals having such a coverage property, this one has the shortest length. Okay, and in today's talk, what I'm going to do is to extend this classical result to a modern setting where the data may have outliers or contaminations. I'm going to consider the setting that is called Hoover's epsilon contamination model. So instead of assuming data are generated from a single distribution, here in this setting, there will be an epsilon fraction of outliers that are generated from this contamination distribution Q, which may or may not be related to normal theta 1. Okay? And I want to emphasize that in Hoover's setting, it is very important that the contamination distribution Q does not have any assumption. It can literally be any distribution. So you can basically think of the outliers, which are epsilon fraction of the data. They can just take arbitrary numbers. Okay? And the parameter epsilon, I'm going to call it by the contamination proportion. And I'm going to ask the same question. Now, with the presence of outliers, how can we still construct confidence interval for the location parameter theta? Okay? So before talking about incident quantification, perhaps I can briefly review what we know about estimation. This is nowadays quite well known. The sample median is a rate optimal estimator for the median. It is for the location parameter. It is robust. It achieves this high probability error bound. So for median, the error can be shown to be bounded by this rate 1 over root n plus epsilon with high probability. So you can see, in addition to this 1 over root n parametric rate, you also have this additive term epsilon that characterizes the influence of contamination. Right? So this additional term epsilon cannot be avoided because you can also prove 1 over root n plus epsilon is the minimax rate of estimating the location theta under Hoover's contamination model. So the sample median is a rate optimal estimator in this setting. So now if you want to do confidence interval construction, one thing you can do is to rewrite this high probability error bound into the following confidence interval, right? So now you have an interval that is centered at the sample median. The radius is given by the rate 1 over root n plus epsilon. And obviously, this is a good construction because it satisfies the coverage property because the two probability events are exactly the same. And the length of this construction is also rate optimal. You can prove that the length of a confidence interval cannot be shorter than a high probability error bound, right? So this is actually an optimal construction. Well, the only problem with this construction, though, is very easy. It's that it requires the knowledge of epsilon, right? So yes, the question.
Epsilon here, so is it displaying epsilon or it's expansion on small parameter?
I'm sorry, could you repeat?
So is the epsilon assumed to be small and that's asymptotic result, or it's an exact result for any epsilon?
A very good question. Thank you for the question. So here, the result is not asymptotic. The result holds for for all n and epsilon as long as 1 over root n plus epsilon is sufficient small, say smaller than some a universal constant. But you can also think of the asymptotic setting where epsilon may be a function of the samples, right? So you can just plug in whatever epsilon as a function of n. For example, if epsilon equals 1 over root n, then you just get the parametric rate. But in general, this is not asymptotic. Exactly, no assumption. Okay, that's why you have this additional term in addition to the error bound. Otherwise, you can do better. Okay, thank you. Okay, so now let's take a look at this very simple construction, right? So in order to write down this confidence interval, you obviously need to know the value of epsilon, but that's the problem. In practice, epsilon is not known. Well, you may be wondering, is it possible for us to estimate epsilon first from the data and then do a plug-in, right? Well, the problem is, I just said the contamination distribution Q does not have any assumption, right? So that means the parameter epsilon is actually not identifiable. So estimation of epsilon would be impossible. Nonetheless, I'm still going to ask the question, if epsilon is unknown, is it still possible for us to construct confidence interval for parameter theta? Okay, that's the question of today's talk. So let me first try to lay down all the mathematical ingredients that I want. What we need is a random interval C hat that is a function of the data x1 through xn, and we can write down two requirements. Right? The first is the coverage requirement. It says that the confidence interval C hat needs to contain the true parameter, say with probably 95%. And we also have a length requirement that says the length of the interval is bounded by some function r with high probability, right? So this length function r is a function of both the sample size n and the contamination proportion epsilon. And since I want to deal with the situation where the contamination proportion epsilon is unknown, I'm also going to take in Feynman for epsilon over the entire interval 0 to 1 over 2. So these two properties hold uniformly over all epsilon, okay? And whichever C hat that satisfies these two properties simultaneously, I'm going to call it by an adaptive and robust confidence interval. So the question we are going to ask today is, among all adaptive and robust confidence intervals, which one has the shortest length? Okay, in other words, in this framework, what is the smallest function r that I can put here? Okay, so I hope the question is clear. Let's take a look at this result. So we show that, at least in the Gaussian case, any adaptive confidence interval that satisfies the coverage condition, its length must be lower bounded by this function that contains two terms, 1 over root log n and 1 over root log 1 over epsilon. Okay, I really want you to compare this rate to the previous non-adaptive rate, 1 over root n plus epsilon, that can simply be achieved by the median construction, right? So if you actually know the value of epsilon, you can just use the median confidence interval, and you can achieve this polynomial rate in terms of the length. But the theorem says that if you do not know the value of epsilon, you cannot do better than this logarithmic rate, right? So there is a huge difference between these two rates that characterize what is known as the adaptation cost. Okay, so think of the situation where epsilon is 0. Epsilon equals 0, that means there is no contamination, right? You just get 100% clean data. Then, then the second term will vanish because epsilon is 0. But the problem is you still have the presence of the first term, which is of order 1 over root log n, and compare with the parametric rate 1 over root n. Now, in order to achieve the same accuracy of incident quantification, you have to collect exponentially more samples just because you do not know epsilon, right? So, of course, epsilon may be 0, but the problem is you do not know whether your data is clean or not. So you still have to pay this cost. Okay? And in addition to this lower bound result, we also have an explicit construction of the confidence interval that is based on the empirical CDF. The inverse of the empirical CDF is called the empirical quantile function, which are basically all the statistics at different levels. So this particular construction based on quantile function or all the statistics at different levels is going to do the work, right? So if you take a look at the formula, it does not depend on the contamination proportion epsilon. It is fully data-driven. And since the computation is based on all the statistics, right? So the computation can be done very efficiently. You only need to sort the samples. And we show that this construction not only achieves the coverage, but its length is bounded by the previous lower bound. So this is an optimal construction. Yes, please.
If you're willing to make assumptions, does that one over square root of any?
Great. Of course. If you are going to make some assumption on Q, yes, the 1 over log n is possible to be improved. And what's more, even the minimax rate of estimating theta can also be improved. Okay, so for example, there are all kinds of examples in terms of the contamination distribution Q, right? So in today's talk, I'm going to focus on the worst case situation. There's no assumption on Q, so the outliers can be arbitrary. But let's say Q is a symmetric distribution around theta, okay? And in that setting, you can not only show the minimax rate can be improved, you no longer have this additive term epsilon in the minimax rate of estimation, but then what's more, the adaptation cost of confidence interval is also different. I'm happy to give you more details offline. This is a very different problem, and thank you for the question. Okay. All right, so if you look at this formula, you may be wondering, right, so how can I derive this formula? Is it something that is from, I see another question. Yes, please. Yeah.
Well, about the lower bound of the opposite.
Yeah.
I think the horizontal distribution being Gaussian seems quite strong because, in that case, we can use Gaussian CDF and those kind of things.
Exactly.
If we have even worse, then the log n may not be the lower bound, and we have an even smaller lower bound.
So the question is, the construction seems to depend on the Gaussian assumption because here we have the Gaussian CDF, right? So what if we do not have the Gaussian assumption? I will address that in later slides. That's a very good question. Any other question? Okay, good. All right, so several questions we need to address, right? So first of all, how do we derive this formula, okay? So is it some general principle that we can follow? And second, why do we have such a huge cost of adaptation when we do not know epsilon, okay? And in order to address these questions, let me talk about related hypothesis testing problem, which I think is the mathematical essence of the construction of confidence interval. So the hypothesis testing problem I'm going to consider is this one. The null hypothesis says the data is generated from normal theta 1. Alternative says, okay, the location has a shift. It's no longer theta, it's theta plus r, right? In addition, you're going to have 50% contamination in the alternative, okay? So not only are you trying to distinguish theta versus theta plus r, you will also try to tell the difference between clean data and data with 50% contamination, okay? And here I want to emphasize that in this formulation, both the numbers theta and r, they are fixed. In other words, the null hypothesis is simple. It only contains a single distribution. On the other hand, the alternative hypothesis is composite because Q is allowed to vary, right? So to be more precise, the alternative contains any distribution that can be represented as such a mixture with some Q. And the goal is to find the smallest r such that the null and the alternative can still be separated with NID samples. And this smallest r is going to be called the minimax separation of the testing problem. Okay? So the reason I want to solve this testing problem is because of the relation to the construction of the confidence interval here. So pay attention. Here, this is just a special case of the general construction of confidence interval because epsilon only takes two values, right? So either epsilon is 0 or epsilon is 50% because the corresponding testing problem is trying to distinguish between 0 and 50%, okay? The precise relation goes as follows. Suppose you can solve the testing problems. Then, yes, a question, please. So R is a number. Yeah. Okay, so here R is just a number, right? So, but I'm going to, the goal is try to find the smallest R such that you can distinguish null and alternative. And that smallest R is going to be a function of the sample size. So in the end, we will try to derive the optimal rate of R as a function of N so that the problem can be solved. Yes.
Is equal is given by the theta hat. And this the adaptive is interval in this setting. I'm a little confused why it's called adaptive or not.
Oh, adaptive means this formula, if you want to compute that, you don't need to know epsilon. So adaptive means adaptive to the knowledge of epsilon, right? So now, even you do not know epsilon maybe 10%, maybe 0, maybe 30%, it doesn't matter, right? So you can always use this formula. It's the same formula, but the property is if the data is actually clean, say it has a smaller epsilon, then the length of the interval is automatically going to be smaller. That's the meaning of adaptation. Okay, thank you. Yeah. Exactly. Yes, yes. We know that the majority of the data is from normal theta 1. Yeah, good. Thank you. All right, so let's go back to the relation between the testing problem and the construction confidence interval. The relation goes as follows. If you can solve the testing procedure, right? So you have this testing function with small type 1, type 2 error. You can, let's say you have a confidence interval then with the coverage and the length property. You can actually turn this confidence interval into a testing procedure by rejecting the null hypothesis whenever the alternative parameter is contained by the confidence interval. Okay? Then as long as here you have small alpha and beta, this corresponding testing procedure will also have small type 1, type 2 error. The opposite direction is also true. Suppose you can solve the testing problem, then you can invert the testing procedure to get a confidence interval by including all theta plus r such that the corresponding alternative hypothesis is accepted. Okay? So basically, these two problems are equivalent. So having understood the equivalence between the two problems, let's just focus on solving this testing problem. And without loss generality, I can just assume theta to be 0 because this is location family, right? So how can I solve a testing problem like this? Well, it follows a standard recipe. So, right, so I'm trying to propose a testing statistic. What I want to show that is that the testing statistic is small and the null, but large and alternative. If this is true, then I can just reject the null whenever the testing statistic exceeds certain threshold. Okay? The particular testing statistic I'm going to use is the indicator function that characterizes the information of the distribution at the tail. Okay, so let's try to take a look at the magnitude of this indicator in the both null and alternative. And then now it is just the Gaussian tail probability, right? So it have this exponential tail behavior, a double exponential tail behavior. Let's take a look at the expectation under the alternative. Well, since I do not have any assumption on Q, the only inequality that you can write down is this one, right? The magnitude of the indicator under the alternative is given by the contribution from the first component. So you have the mixing proportion 1/2, and again multiplied by the Gaussian tail probability, but this time you have a location shift R that goes into the exponent. Okay? So what you want is that the expectation and an alternative is much greater than the expectation in the null. Then this statistic has separation at least in the population level. Okay? But actually, if you want to do the hypothesis testing, you don't have access to these expectation numbers, right? So you only have access to the empirical version, which is the empirical average of these indicator function. So what you also need is the concentration between the empirical average and expectation, right? And since here we are dealing with the empirical average of these indicators, and the indicator is binary, right? So it is just a Bernoulli random variable. So what we want is the concentration between the empirical average of Bernoulli random variable and the Bernoulli mean, right? So we know that the empirical average of Bernoulli random variable has the same order as its mean if and only if the Bernoulli mean is of order at least 1 over n. Okay, so you can write down this requirement to make sure that you have concentration between the empirical and the population version. Okay, so once you have these 2 requirements, you can solve for t and r. Right? For example, to satisfy the first requirement, you only choose t to be of order root log n. And once you plug the choice of t into the second requirement, you can show that whenever r is greater than the order of 1 root log n, then the 2 hypotheses can be separated using the average of the indicator function. And if you still remember the previous result, the 1 root log n is precisely the optimal length of the adaptive confidence interval when epsilon is 0. Okay, this is how you can solve the upper bound direction of the problem. Now let's go to the lower bound. In the lower bound, what we want to show is if r is small, then you can no longer distinguish between the 2 hypotheses. So the idea is to construct some distribution Q such that the null and alternative, they look similar. Okay, and how do I find such a Q? Well, here's a very simple approach, right? So you try to find a Q such that null and alternative, they are exactly equal. So this gives you the equation that null equals 1 over 2 times this distribution plus 1 over 2 times Q. So if you solve that, here's the solution, that the density of Q equals 2 times the density of normal 0, 1 minus the density of normal R1. Okay? But pay attention here, I put a question mark here, right? Even though this is a solution, this function is not a valid probability distribution, right? So in order that I have a valid construction of the probability distribution, I need this to be a density function, which first of all need to be positive, and second, the integral must be 1. If you check that the integral is 1, but the function may be negative, in fact, no matter what the value of r is, you can always find an x such that the value of this function is actually negative. So you have to fix this issue. The fix is actually quite simple. Is by the idea of truncation, right? So I'm not going to use this function for every value of x. I'm only going to use this function for x that is between this interval from negative t to t. Outside of the interval, I just take 0 as the function of density. Then after renormalization, I make sure it has integral 1, so we get a valid construction of the density function, right? So here what I need is only the positivity of this function when x is inside this bounded interval, right? So this is equivalent to, again, the comparison between the 2 Gaussian tails for all x is, the absolute value is more than t, right? But because of the truncation, right, so I no longer have the exact match between the null and the alternative, right? So I cannot say the alternative is exactly the null. It's only close to the null, right? So there is an approximation error. What I need is that the chi-square divergence between the null and the alternative is bounded by the order of 1 over n, because if you are familiar with Lacan theory, right, so this is the sufficient condition to guarantee that if you have ID data, it cannot distinguish between the null and alternative hypothesis. Okay? Now, if you compute this chi-square divergence, since the error is, the majority of error is coming from the truncating of the Gaussian tail, right? So if you compute the chi-square divergence, it's basically determined by the Gaussian tail. So what you need is the Gaussian tail to be bounded by 1 over n. So again, this is going to be satisfied by choosing t to be of order root log n. And if you plug the choice of t into this requirement, you can show that if r is smaller than the order of 1 over root log n, you cannot separate the 2 hypotheses, right? So this is the lower bound construction, and it's very much like the same calculation that you have seen in the upper bound. So 1 over root log n is actually the mean max separation rate for the testing problem. Okay, so let's summarize. For this testing problem, we have a rate optimal testing procedure that rejects the null hypothesis whenever the average of this indicator exceeds certain threshold. So here I take the threshold to be twice the expectation of the statistic under the null hypothesis. Okay? As I said, if you have the testing procedure, you can turn it into a confidence interval according to this formula, right? So let's take a look at what the confidence interval looks like. And by the definition of the quantile function and the CDF, this is all theta plus r such that theta is bounded by the quantile function of some level minus t. Okay, so after change of variable, this is all theta that is bounded by this quantile function minus t plus r. Okay, so at this point you may be wondering what's going on, right? So this is just a one-sided confidence interval. Where is the other side? But remember, we are dealing with a testing problem that is also one-sided, right? So if you want to get the other side of the confidence interval, you also need to solve another testing problem where the alternative hypothesis is theta minus r. But the derivation of the testing procedure for the other side follows exactly the same mathematics. So I'm going to just ignore that, right? So let's just focus on the right side endpoint, okay? So to summarize, this is the formula of the right endpoint of the confidence interval. And remember, previously, we chose t to be of order root log n, and r to be of order 1 over root log n. So the relation between t and r is r equals 1 over t, right? So if you plug in this relation, then you get this very clean formula that only depends on the choice of t, okay? All right, as I said earlier, if you can solve this testing problem, it will lead to this confidence interval that is adaptive only over 2 levels of epsilon, right? Either epsilon equals 0, no contamination, or epsilon equals a half, 50% contamination, right? If you want a confidence interval that is adaptive over all levels of epsilon, it turns out you actually need to solve a slightly more general hypothesis testing problem where the contamination proportion into the null is a general epsilon. But the good news is that it turns out the solution for this slightly more general testing problem is exactly the same formula. The only difference is now the choice of t needs to depend on both epsilon and the sample size n, right? So if you give me a different level of epsilon, I can solve the testing problem with the different levels of t. Okay, so in the end, if I want to get a confidence interval that is adaptive over all levels of epsilon, the trick is to apply this intersection over all levels of t. Okay, so in the end, we arrive this formula of confidence interval. If you also derive the other side, that is a very optimal construction to this to the problem that we want to solve. Okay. Any question at this point? Yes, please.
The H1 remains the same, and you again have Q in the null.
Yes. So what we also can show is if you solve this confidence interval, then it actually leads to the construction of the confidence interval that is adaptive over epsilon and 1 over 2. Okay? So in the end, this is a formula that solves a collection of the testing problem for all levels of epsilon and the null simultaneously. And as a result, it is going to be adaptive for all epsilon. Yes, exactly. So here, half, under the alternative hypothesis, right? It's always the largest value of epsilon. Yeah. So this half is special. Thank you. Any other question? All right. So I think now we can come back to your question, right? So at this point, we have been focused on Gaussian distribution. And for some of you may have already realized that this is very much dependent on the Gaussian assumption, and the rate 1 over log n is precisely coming from the Gaussian tail. Yes.
Sorry, for that,
Yeah.
when epsilon is low, we know the median achieves kind of the optimal.
Yes.
Oh, and does this estimator has
Yes, actually, if you take t to be constant or even t to be 0, right? So this is almost using the median, right? Median is basically quantile of level 1 over 2.
I can kind of interpret it as you're kind of aggregating over medians over different epsilon levels.
Aggregating over different levels of quantiles, right? And median is a particular quantile. So the theory says if you do not know epsilon, now you have to use all levels of quantiles. Very good. All right. So what about other distribution? What if we are dealing a distribution that is non-Gaussian, right? So let's take a look at this example, right? So this is called a Laplace distribution. Let me remind you that the Laplace distribution does not have a Gaussian tail. Instead, it has an exponential tail, right? So maybe the theory could be different. So we are still going to ask the question, how can we construct a confidence interval for Laplace distribution if epsilon is unknown? Well, it turns out it's kind of surprising that if you have Laplace distribution, we can show for any adaptive confidence interval, right? The length can no longer be better than a constant. So this is very bad, right? So it says even if you have epsilon equals 0 and it's infinity, right? So this is saying you may have an endless supply of clean data, but just because you do not know the data is clean or not, the best confidence interval cannot shrink, the length cannot shrink as the sample size goes to infinity, right? So the sample size no longer matters, okay? So what's happening here, right? So why is it so different from the Gaussian case? Well, again, let's take a look at the corresponding testing problem, okay? So here I'm trying to distinguish this Laplace with with mean 0 versus Laplace with mean r, but with 50% contamination. It turns out for the Laplace distribution, you can actually find a Q such that the null and the alternative, they are exactly the same without doing truncation. Because the solution to the equation that null equals alternative, which is this formula, is a valid construction of density function. It stays positive for all x as long as r is bounded by log 2, right? And log 2 is a constant. That's why you cannot do better than constant. Okay? So here are two situations. The first situation is the data is all generated from Laplace with mean 0. The second situation is data is generated from Laplace with mean, say, log 2, but you have 50% contamination. But here the construction says these two distributions are exactly the same. They are the same, right? So if I do not tell you whether the contamination proportion is 0 or 1 over 2, you do not know whether the mean is 0 or r. Okay, that's why confidence interval length cannot be better than constant. Okay, for Gaussian, you cannot do that. That's why Gaussian is different. And actually, we take a look at many other distributions. Here, I order them from heavy tail to very light tails. T distribution has polynomial tail. Here is generalized Gaussian. It includes Gaussian and Laplace with beta equals 2 and beta equals 1. Modified and based, these are distributions with bounded support. So for modified distribution, one nice feature is that the density is analytically smooth even at the boundary. Base distribution is defined as the convolution of independent uniform. So k equals 1, that's just a uniform. K equals 2, the density function has a triangle shape. Okay, so for all the corresponding location family, if we want to do inference for the location parameter, right? So if you only want to estimate the parameter, they're all the same. You just use the sample median, and for each different cases, right? So you can also prove a matching a minimax lower bound showing that the median is rate optimal. And if you want to construct confidence interval, and you know epsilon, then the confidence interval centered at the median is going to work. The length is also given by this rate. But if you want to construct confidence interval, but you do not know the value of epsilon, then they are all different. It's case by case. And for T distribution, its tail is even heavier than Gaussian. The rate is constant, right? So it's very much like the Laplace. And for generalized Gaussian and modify, you get logarithmic rate. And for base distribution, you can even get polynomial rate because there are lots of information at the boundary. Okay. And I want you to pay attention to this rate, and in particular this exponent. The numerator of the exponent is the positive part of beta minus 1, right? So this rate goes to 0 as n goes to infinity if and only if beta is strictly greater than 1. That means the Laplace distribution is actually the boundary between what is known as the shrinking confidence interval versus non-shrinking ones, right? So an adaptive confidence interval can shrink to 0, the length can shrink to 0 as the sample size goes to infinity if and only if the tail of the distribution is lighter than that of Laplace. Okay? All right, so that's basically what we know about the location family. You may be wondering, what about other problems, right? So there are other statistical models that go beyond the location family. Well, which I will address. It's actually this is the second part of the talk. You have another question, please. Yeah, please. I appreciate that. Yeah. Yeah.
Seems like if k goes to infinity, it shrinks to constant.
Oh, here we are dealing with k as a constant, right? So if k goes to infinity, you better standardize this one. Then you have such a limit theorem, then it should go to Gaussian. So if you consider k as a growing function of n, we haven't worked this out, but we should expect a theory for large k, then the rate will interpolate between this one and the Gaussian rate. Very good question. All right, so my plan is to go beyond the location model. But before I move to the second part, I think I want to address this issue still in the location model, right? So previously we assume, at least in the Gaussian case, the variance is it needs to be given. It's 1, right? What if the variance is unknown? What if we have a general scale parameter? Then what happens, right? Let's just consider this more general model, and we have a sigma square here, which may not be 1, okay? So first of all, let's consider the case where sigma square may not be 1, but it is actually known, okay? So if you know sigma, this is very easy. You can always do this scaling argument. So this scaled version of the optimal construction is going to work, right? So this is almost trivial. You can still show that the scale version of the confidence interval still achieves the rate optimal length. Okay, so when sigma is known, it's very easy. If sigma is unknown, what we also know is you can actually estimate sigma by a robust estimator, right? So if you want to estimate sigma with the presence of outlier, what do you do? Well, you can use what is known as median absolute deviation, right? So this is a robust estimator for the scale parameter. It does not exactly estimate sigma. It estimates something proportional to sigma, but you can always scale the estimator to make sure it actually estimates sigma, right? So then you can prove it has this error bound, 1/√10 plus epsilon. And this 1/√10 plus epsilon, you can also show it is minimax rate optimal, okay? Now I want you to compare these two rates, right? So it turns out the estimation error of sigma is much faster than the optimal length of the confidence interval for theta, right? So if you notice that, it's naturally it's very intuitive to expect that just by plugging sigma equals sigma hat, it's going to do the work, right? This is exactly what I told my collaborator Viet-Tien, it should work. Why don't you just go back and prove it? The next day he came to me, he said, it doesn't work. I was like, what do you mean it doesn't work, right? So let me just say the intuition again. You see, the estimation error of sigma is polynomial, but the optimal rate that we are going to achieve is just logarithmic. So the error is basically negligible. The plugging should work. technically, you cannot prove it. Maybe there is dependence when you do the plugin. Why don't you just do sample splitting, right? So you split the sample into two halves, use the first half to estimate sigma, and then second half to the plugin. He said, I already tried it. It doesn't work. All right, so at this point, now we started to take the problem more seriously. It turns out he was correct. It doesn't work. And not only that, we eventually show nothing works. Okay? The subtlety of the problem is summarized into this table. And I want you to take a look at this entry. It says, if you do not know epsilon, and on top of that, you do not know sigma either, then we can show the optimum length of count interval is just constant, does not depend on sample size anymore. So this is very much like that you just saw in the Laplace case. Okay? And if you compare the first column and the second column, there is a huge contrast, right? So if you know the value of epsilon, then it doesn't really matter whether you know sigma or not. It's all the same. But if you do not know epsilon, then additionally you do not know sigma, then you would have additional adaptation cost. That's a subtle difference. Yes, please.
So I mean, this can kind of connect this to the Laplace case because the Laplace can be that the scale mixture of the normal field. With a mixing distribution sigma, you get to the Laplace.
I think it's really case by case. If you let's suppose you know this mixing distribution, right? Then as the previous the previous table, the big table suggests, it will depend on the tail of the Gaussian scale mixture, right? So if the tail is exactly like Laplace, then it's like that. But if the tail is lighter, then you can still do something, okay? So that's the answer to your question. But here we actually, the result is actually even stronger than it looks. So we can even say, if I even tell you sigma is either 0.9 or 1, okay? You do not know which one. I tell you it's one of the options. It is still answer. You cannot do better than constant. Because the lower bound is based on 2-point construction. Yes. That's a completely different story, right? So it's very different. Yeah. Yes.
Can build another distribution so that the alternative that you are building that matches with.
Oh, exactly. Yes, this is exactly correct, right? So previously we saw that when sigma is known, so in the corresponding noun and alternative, both variants are 1, so you cannot have a Q that exactly match noun and alternative, right? So now if you have different sigma under noun and alternative, you can actually do that because it's possible to hide one Gaussian beneath another if the two sigmas are different. This is precisely the correct intuition. Thank you. Okay, so the result is it's a bit disappointing, right? So because in practice you never know sigma, so it suggests that well in practice, either you can do nothing, or maybe you should really think again. Do you really know nothing about Q, or there's something that you should explore, right? So the result says some assumption on Q is necessary. That's how I interpret the result. Okay. All right, so let's try to briefly talk about other models, go beyond the location model. Let me start with the Bernoulli model because this is the simplest example, right? So we can ask the same question for Bernoulli distribution with contamination. How do you do adaptive confidence interval? Okay, this is actually quite simple, and I think I give you 5 minutes, and every one of you can solve that. First of all, you can easily convince yourself that the worst case contamination distribution Q should also be Bernoulli. Well, because suppose for some reason Q generates, say, 2, right? Obviously, you know it's outlier, you just throw it away. So without planarity, I can always assume Q only generates 0, 1, so that means it must be a Bernoulli distribution. And if it's Bernoulli, then we know Bernoulli is linear in terms of the parametrization, right? In particular, Bernoulli half can be written as a mixture of Bernoulli 0 and Bernoulli 1. So now if you have a binary sequence with roughly 50% 0, 50% 1, you really don't know whether it is actually generated from Bernoulli with probably a half, or it is actually generated from Bernoulli with probably 0, but you have 50% contamination. And if I do not tell you whether the contamination proportion is 0 or 1/2, you don't know whether the mean is 1/2 or 0, right? So for Bernoulli, you cannot do better than constant if you do not know epsilon, right? So that's it. The problem is solved. The conclusion is it's, you know, you cannot do better than the trivial one. So it's not very interesting, right? So what about binomial? For binomial, at least we should expect something interesting can happen, because if M is large, then by central limit theorem, binomial is very much like Gaussian. And for Gaussian, we know you can do something. So at least for binomial, for large M, something is possible, right? So this is exactly correct intuition, and we show that the optimal length of the adaptive count interval for the binomial mean takes this formula, right? So it has two terms. The first term is precisely the Gaussian rate. Of course, you have this scaling factor because of degrees of freedom m, but you also have the present second term 1/m. Okay, let's say m is a constant, then you have a constant rate. The sum is a constant, so this recovers the Bernoulli as a special case with m equals 1. Okay, so as m grows from 1 to infinity, this sort of nicely interpolates between the Bernoulli rate and the Gaussian rate. Okay, of course, I can tell you the construction of upper and lower bounds for the binomial case. I think they are interesting because it's no longer location model, so the inversion of the testing function strategy does not really work here. You have to do something that is extra. But I decided to skip that and talk about a different model. In fact, the reason I tell you this result is to prepare you for the next example where I want to talk about what happens if you have network data. So let's consider the simplest network model, which is called Erdo-Shreni model. So Erdo-Shreni model says for every edge, it's either connected or not according to a Bernoulli probability with parameter p, right? So let's consider Erdo-Shreni model with contamination. Okay, so when it comes to network model with contamination, there are two choices. One is called edge contamination, that says there is an absolute fraction of edges that are contaminated. But if you think about that, this is exactly equivalent to the previous Bernoulli case, because the adjacent matrix, you can just expand that into a sequence, and it's not mathematically interesting. Mathematically more interesting, there is a notion called node contamination that says an absolute fraction of the network nodes are contaminated, and all the edges connecting to the nodes that are contaminated are arbitrary. So in terms of adjacent matrix, this says that there is an absolute fraction of rows and columns that are contaminated, right? And for the block that is not contaminated, then you have RID Bernoulli P. Okay, I really want you to compare this model to a different model. This is a matrix observation, but you only have row contamination. You don't have column contamination. Okay, and in the second case where you only have row contamination, this is actually equivalent to Huber's model. Okay, the reason is if you have a row that is not contaminated, then the sufficient statistic for P is the summation of the parameter, which exactly follows binomial. Okay, so this is actually equivalent to the previous binomial model with m equals n. Okay, now these two models look similar, right? So the question is, are they actually similar, or there are some subtle difference? So it's summarized in the table. If you only care about estimating the parameter, it turns out it's very much the same, right? So the minimax rates you can prove for both models are 1/√10 times 1/√10 plus epsilon. Okay, for Huber model with binomial distribution, you can show the minimax rate of estimation is this rate. This is not very hard to prove if you are familiar with standard techniques of constructing rate optimal estimator for Huber's model. However, for a Schweini model with node contamination, even though it has the same rate, this is actually highly non-trivial to prove. It takes an entire paper by Acharya, Jain, Kamas, Suresh, and John back in 2022 to prove it. It's a very smart idea. The paper is a non-trivial piece of work. On the other hand, if you talk about confidence interval construction and you do not know epsilon, it turns out they're different. Okay, in the first case of binomial, right? This is exactly a special case of the previous theorem. By taking m equals n, you get a Gaussian rate. But on the other hand, if you have a Schweini model with node contamination, then the optimal radius for confidence interval has the rate 1/√10, right? So there is a difference. Okay. Now, if you look at this 1/√10 rate, you may be wondering, hey, this is not bad, right? 1/√10 goes to 0 pretty fast. But I want to emphasize that this 1/√10 rate is actually the worst rate that you can expect for this problem, because it is exactly the rate by taking epsilon equals constant, say 1/2, in the estimation rate. Okay? So this is saying now if you do not know epsilon, just pretend epsilon takes the largest value, say 1/2. Then do whatever as if you know epsilon equals 1/2. Just act completely conservative. And since it is already optimal, it says the most conservative strategy is optimal. So that means adaptation is completely impossible. Okay? Please, question.
Contaminated by the node contamination. How is it defined? You see, with the upper model, there is an explicit definition outside of the epsilon plus epsilon q. But for the Schweini model, how is it defined?
So you first have the Schweini model. You write down the adjacency matrix. Okay, the adjacency matrix is n by n. Then you randomly select an epsilon fraction of indices. So according to these indices, it corresponds to epsilon fraction of rows and columns. Okay, and for all these entries, you replace the original entries by arbitrary binary numbers. That's how the contamination is done.
Some vertex, and then replace with some other vertex, like that.
It's not I replace the vertices, it's I replace all the edges that are connecting to these vertices. Yeah. And in the second model, you can think of that as a directed network, right? Then I only replace, say, all the incoming vertices, right? So that's why only the rows or maybe only the columns are contaminated.
The number of vertex is always fixed, the little n.
Yes, the vertices are fixed. Yes, the nodes are fixed. Okay? The contamination is on the edge. Okay? Of course, you can always consider, so this is called node contamination, right? But you can always consider edge contamination. As I said, edge contamination is actually very easy. So that's why we don't deal with that mathematically. Thank you. Okay. All right. So why is there such a subtle difference between the two cases, right? Again, let's take a look at the corresponding testing problem, right? So here I'm trying to distinguish between the two hypotheses. The now is Schweini graph with parameter p. Alternative is Schweini graph with parameter q, but you have 50% contamination. Okay, I want to design the contamination patterns so that the two hypotheses is hard to tell the difference. The particular pattern I'm going to consider is this one. And for those of you who are working in network analysis, especially community detection, then you may recognize this is called a stochastic block model. Okay, and if you look at the literature, it is known that if you try to distinguish between a Schweini model and a stochastic block model, then it is necessary that that P and Q needs to be differ by the order of 1/√n at least. Okay? And in fact, we can show if we have an adaptive confidence interval for the Erdős-Rényi model with node contamination, then you can turn this confidence interval into a testing procedure that can distinguish between Erdős-Rényi model and the stochastic model. Therefore, the lower bound for the testing problem is also a lower bound for the construction, for the length of the confidence interval. Okay? All right. How many minutes do I? 1 minute? Okay. So let me wrap up, right? So another point I wish I can discuss is multivariate parameter, right? So we all focus on one-dimensional parameter. If it's multivariate, we can talk about confidence set. All right, so if you do confidence set, you can talk about optimal radius, right? So the point is that, for example, for this model, we can talk about optimal confidence set for the vector theta. Okay, it turns out, just from information theoretic perspective, you can also construct a optimal adaptive confidence set for theta when epsilon is unknown. It has a rate optimal radius, which measures the size. But the problem is this construction is not computable. If you want to compute it, it's NP hard. Okay, so what we can prove is that for this problem, if you want to construct a radius optimum confidence set in the multivariate case, at least among all SQ algorithms, you cannot do that. You cannot do better than constant radius. Okay, so that basically the intuition, the interpretation is the problem is only possible if you consider exponential time algorithm. If you consider polynomial time algorithm, then nothing is possible. Okay, if you are willing to believe SQ algorithms covers the class of polynomial time algorithm. Okay, so in the multivariate case or the high-dimensional case, when epsilon is unknown, not only do you have an information cost, but you also have a computational cost. Okay, that's a difference. That's a huge difference compared with the situation where epsilon is known. Okay, so I'm going to skip the last point and thank you for the attention.